Going to be Vodcast E4, and we're going to start talking about hormones that are outside of the direct control of the pituitary and hypothalamus. Let's take a look at concept number 4 first. Non-pituitary hormones help regulate body metabolism, homeostasis, development, and behavior. And there are many non-pituitary hormones, but we're only going to talk about a few of them. The ones that we're going to look at are the ones that are important in regulating various functions of the body. So if you remember, hypothalamus, pituitary gland, and also the pineal gland is up in the head, up in the cranium. The thyroid gland and the parathyroid glands are located in the neck, anterior of the trachea. And the pancreas is located in the abdomen, kind of part of it on top of the liver on the left side of the body. The thyroid gland consists of two lobes located on the ventral surface of the trachea. It produces two iodine-containing hormones. One's called T3 and the other's T4. T3 is triiodothyronine. Triiodothyronine, that's T3, and thyroxine, which is T4. You need to make sure you can separate those two in your notes. These systems work on feedback loops, and if you remember feedback loops, this came from Chapter 1, positive feedback and negative feedback. And in this particular situation, we work on negative feedback loops. So we're going to be looking to reduce the amount of iodine that's in the blood. So the hypothalamus, at any rate, is the command center, and it works with two antagonistic hormones. Oops, got ahead of myself here. Looking at T3 and T4, the hypothalamus senses that there's too much T4. So it's going to want to reduce the amount of iodine that is in the bloodstream. So it's going to send a signal to the anterior pituitary gland, which deals with the thyroid sensing hormone, TSH, and it's going to instruct the thyroid to collect iodine and store it in the thyroid gland. T3, on the other hand, deals just with the anterior pituitary. The hypothalamus is not directly involved in this, and if there's too much T3 in the bloodstream, the anterior pituitary gland is going to send its hormone out, the thyroid sensing hormone, and it's going to instruct the thyroid gland to store T3 in the thyroid gland, and there are special cells where that happens. The parathyroid hormone and calcitonin are the controls for blood calcium. These are two antagonistic hormones, one in the parathyroid hormone, and that's PTH, the parathyroid hormone, and calcitonin, which is in the thyroid gland. And they play a major role in calcium, Ca2, the ion of calcium, in a homeostasis, so that it's trying to maintain a very tight balance of calcium in the bloodstream. You need to review this chart either here on this slide, or you need to look in the textbook, because that's going to be on the test. I'm going to expect you to be able to draw this and describe it. I'm going to go over this in class very quickly on Tuesday to make sure that we have it. Calcitonin, of course, is secreted by the thyroid gland, and it stimulates the deposition in the bones. So that means it's taking calcium out of the blood and building bone, and by doing that it lowers the blood calcium levels. It also reduces secretion of calcium by the kidneys, and again that supports a lowering of blood calcium levels. The parathyroid hormone, secreted by the parathyroid glands, it has the opposite effects on the bones and the kidneys, and therefore it raises the calcium 2 levels. It also has an indirect effect, stimulating the kidneys to activate vitamin D, which promotes intestinal uptake of calcium from food. So you're getting more and more calcium from your food rather than excreting it through the kidneys. So we're going to go through this in class, because I want to make sure we understand feedback loops. Let's take a quick look at the pancreas. The pancreas controls blood glucose. Now there are three kinds of cells found in the pancreas: alpha cells, which produce glucagon. The beta cells produce insulin, and the delta cells produce somatostatin. I'm sorry, can't speak today. And this inhibits, or lowers, both glucagon and insulin. Well, we're going to spend most of our time on the alpha and beta cells. Insulin and glucagon are antagonistic hormones that help maintain glucose levels for homeostasis. Both of these hormones are found in the islets of Langerhans. We're going to go through this chart as well. This is more feedback loops, and this is how the body is sensing in the pancreas, continually monitoring the amount of glucose that's in the blood. Too much sugar in the blood, too much glucose in the blood, pancreas is going to release beta cells. They're going to be stimulated to release insulin into the blood, and the insulin is going to direct body cells to take up more glucose in the form of glycogen and store it, and it does the same thing with the liver. Once we get to too little glucose in the blood, we're then going to use glucagon, and glucagon is going to stimulate the release of sugar back into the blood. It's going to break down that glycogen. It's going to release it into the blood, and it's the alpha cells that are going to do that. So insulin reduces blood glucose levels by promoting the cellular uptake of glucose, stores as glycogen, slows the glycogen breakdown in the liver, and promotes fat storage. Glucagon increases blood glucose levels by stimulating the conversion of glycogen to glucose in the liver, and then it gets released into the bloodstream. Two diseases that we want to think about. The best known, diabetes mellitus, is the best known endocrine disorder, and it's caused by a deficiency of insulin or a decreased response to insulin in target tissues, and is marked by highly elevated blood glucose levels. Type 1 diabetes, this is insulin-dependent diabetes. This is an autoimmune disorder in which the immune system destroys the beta cells of the pancreas, and therefore you're not producing enough insulin, and therefore you're not storing sugar, not taking sugar out of the blood. Type 2 diabetes is a non-insulin dependent diabetes, and this is characterized either by a deficiency of insulin or more commonly reduced responsiveness of target cells due to some change in insulin receptors. Here's just a quick look at the thyroid and the pancreas, and you can make sure you kind of put this in your notes in a fashion that you can get them back. Okay, so this is a little bit long. It's about 7 minutes 40 seconds. I'm going to let you go. Be prepared to discuss this on Tuesday in class. Thank you very much.